Tonight, we are going to rest beside a strange possibility. It is the possibility that black holes do not only hide stars, gas, light, and time from us. They may also hide the place where our best ideas about the universe stop fitting neatly together. That is the soft mystery we will keep near us, not as a puzzle to solve before sleep, not as a test, not as a lecture, just as a quiet question to lie beside for a little while. Because black holes are often described in hard, dramatic ways. They are called monsters, traps, engines, devourers, cosmic mouths, dark hearts of galaxies. And some of those descriptions are not completely wrong, but they are rarely calm enough for what we are doing here tonight. So let us begin more gently. Let us think of a black hole, not as something angry, but as something patient. Not as a sudden attack, but as a deep change in the shape of reality. Not as noise, but as silence made physical. Somewhere in the dark, far beyond our own small roof of air, there are regions where old stars ended, where matter collapsed, where space-time curved too far inward, and where the universe began keeping one of its most careful secrets. And the secret is not only what falls in. The secret is what the laws of nature do when they are pushed to their edge. If you are tired, that is good. Tiredness is welcome here. You do not need to remember every term. You do not need to follow every sentence all the way to its end. You can let ideas blur at the edges. You can keep only the feeling of them. The room around you is safe. The night can hold the details for a while. All we need to do is move slowly. And maybe the best place to begin is not with black holes at all, but with gravity. Because black holes only become strange after gravity becomes strange. First, for a long time, gravity was imagined as a force in the ordinary sense, a pull reaching across space. It was a useful picture, and in many everyday ways, it still works. Apples fall, planets circle, tides rise. Things move the way gravity asks them to move. But then, in the early 20th century, the idea deepened. What if gravity is not a force pulling objects through empty space? What if gravity is the shape of space and time themselves? This is one of those thoughts that seems abstract at first, and then becomes almost simple once it settles in. Space is not just nothingness. Time is not a separate stream flowing beside it. Together they form a kind of fabric, or a stage, or perhaps a better word, a structure. And this structure can bend. Mass does not sit inside space-time like a pebble dropped into a box. Mass changes the geometry around it. It tells space-time how to curve, and curved space-time tells matter how to move. That old image of a stretched sheet with a heavy ball in the middle is imperfect, but still useful if held lightly. Put something heavy down, and the shape changes. Put something smaller nearby, and it follows the shape it finds itself in. Not because a hand reached out and grabbed it, but because the world beneath it is no longer flat. That is the first calm doorway into black holes, because a black hole is what happens when the shaping becomes extreme. When so much mass is gathered into such a small region that the structure of space-time tips too far inward. When the landscape no longer merely slopes, but folds. Far from a black hole, gravity can feel ordinary. A star and a black hole with the same mass influence distant objects in much the same way. An orbit far away does not always care what kind of object lies at the center. Distance smooths differences. The universe often hides its sharpest truths behind scale. But come close enough, and the difference matters. A black hole is not special because it has magical gravity. It is special because its mass is packed into a region so compact that the future itself is rearranged around it. There is a boundary to that rearrangement. It is called the event horizon. This is one of the most famous phrases in science, and also one of the easiest to picture too crudely. So let us be careful, gentle with it. The event horizon is not a wall. It is not a shell of hard, dark matter. It is not a black globe you could stand on or strike with your hand. It has no texture, no crust, no visible seam written across the sky. It is a boundary in what can happen outside the horizon. A light signal can still move away and reach the wider universe. Inside the horizon, every future path leads deeper inward. There is no ordinary outward return, not because something is blocking the way, but because the geometry no longer offers that direction as a real future. That is such a beautiful and unsettling idea that it is worth slowing down over. A black hole does not merely trap things. It changes what counts as escape. Imagine standing in a valley at night. There are slopes, ridges, paths, openings. You can choose this direction or that one. But now imagine descending into a landscape so strangely shaped that there comes a point where every path still available to your future leads downward. You are not fenced in. The terrain itself has taken choice and quietly narrowed it. That is closer to the spirit of the event horizon, and for a sufficiently large black hole, crossing that boundary might feel almost uneventful in a local moment. No impact, no alarm, no line of fire, no cosmic gate. A freely falling traveler might notice nothing special at all when passing through. That softness is part of what makes black holes so hard for the mind to hold. The most absolute boundary in the visible universe may be locally smooth. From far away, however, the story looks very different. A distant observer watching something fall toward the horizon would see it slow. The signals it sends outward would grow weaker, redder, more stretched. The object would seem to linger near the edge, dimming toward invisibility. It would never appear to cleanly cross. Yet from the viewpoint of the falling object, no such eternal hovering occurs. The journey continues, clocks tick, thoughts continue. The horizon arrives and is past already. Long before we reach the deepest puzzles, black holes have done something exquisite to our common sense. They have made time disagree with itself. We will come back to that. For now, simply let it settle. A black hole is not only a place where space curves, it is also a place where different perspectives stop telling the same simple story. And before we go deeper, you can let your shoulders soften if they need to. You do not need to hold the whole shape of this, only the feeling that gravity may be less like a hand, and more like a rune, less like a pull, and more like a path already bent. That feeling is enough. At the center of the simplest black hole story lies something called a singularity. It is another famous word, and another one that deserves a softer treatment than it often gets. People sometimes imagine the singularity as a tiny, infinitely dense bead sitting at the center of the black hole, like a cosmic grain of impossible matter. But in physics, the word often means something more subtle and more troubling. A singularity is not necessarily a thing you can describe with confidence. It is where your description breaks, in the mathematics of general relativity. If one follows the equations inward, quantities begin to blow up. Curvature becomes unbounded, density ceases to behave. The theory leads you toward a place where the map no longer gives sensible directions. And that is important, because it means the singularity is not only an answer, it is also a confession. It is where the theory says, I can take you this far, but not all the way. There is something almost comforting in that honesty. Science does not become weaker when it admits its limits. It becomes more trustworthy, and black holes, perhaps more than any other objects, force that honesty from us. They allow general relativity to speak magnificently about horizons, orbits, time dilation, bending light, and the large-scale behavior of gravity. But at the center, the language starts to fail. The sentences go thin. The infinities appear, the map phrase. So when we say there's a singularity inside a classical black hole, we are saying two things at once. We are saying that the equations point toward a region where every inward path ends. And we are also saying that this is likely where the equations themselves must eventually be replaced or completed by something deeper. Black holes are therefore not just strange objects in the universe. They are places where our current understanding comes close to its edge. To make this more steady, physicists often begin with the simplest ideal black hole, the one that spins not at all and carries no electric charge. This is the Schwarzschild black hole, named after Karl Schwarzschild, who found a solution to Einstein's equations not long after general relativity was born. The Schwarzschild black hole is clean, severe, and symmetrical. It is the purest mathematical form of a black hole, in the same way that a perfect circle is the purest form of a loop. It is not necessarily what the universe most often builds, but it gives the mind something quiet to hold. This black hole has one essential property: mass. Its event horizon forms a perfect sphere, and the size of that sphere depends only on how much mass is concentrated within it. Nothing decorative, nothing extra, no hair, as later physicists would say in a different context. Just mass-shaping geometry, so deeply that a horizon appears. There is a particular calm in this. Black holes, for all their mystery, do not require exotic fantasy in order to exist. At least in principle, they arise naturally from ordinary gravity taken far enough, compress enough mass into a small enough region, and the possibility is already there in Einstein's equations. You do not need new magic. You need enough gravity, enough collapse, enough inwardness. And yet the real universe is rarely content with simplicity. Real stars turn. Real matter swirls. Real collapse almost always carries angular momentum. The most actual black holes are not likely to be still, perfect Schwarzschild spheres. They rotate, and once a black hole rotates, the story becomes more fluid. A spinning black hole is described by the Kerr solution. Here the black hole does not merely curve space-time. It drags it. The rotation twists the geometry around itself. Nearby, space-time is not only bent inward, it is coaxed into motion. This effect is called frame dragging. The phrase is gentle, almost domestic, and it helps. The black hole drags the local frame of space-time around with it. The universe nearby is not quite allowed to remain still. Outside the event horizon of a rotating black hole lies another remarkable region called the ergosphere. In the ergosphere, an object can no longer remain stationary relative to the faraway stars. Even light and matter that try to hold still are swept into participation with the black hole's spin. It is as if space-time there has become a slow whirlpool. And because the ergosphere is not the same as the horizon, something curious becomes possible. Under the right conditions, energy can be taken from the black hole's rotation. This idea, proposed by Roger Penrose, suggests that a particle entering the ergosphere could split, with one part falling inward in a way that reduces the black hole's spin, while the other escapes with extra energy. The details need not trouble us tonight. The calm lesson is enough. A black hole, even while keeping so much hidden, is not completely sealed off from the world outside. Through its rotation, under special circumstances, it can give something back. This is such a lovely correction to the simple image of black holes as one-way endings. They are endings in one sense, yes, but they are also structures, and structures participate. They interact. They shape the space around them in ways that matter. In the deeper mathematics of spinning black holes, the singularity takes on an even stranger form. Instead of a point, it becomes ring-like in the ideal solution. That ring has inspired all sorts of speculation. Could it open onto another region of space-time? Could the interior of a rotating black hole contain paths stranger than a simple final plunge? This is where wormholes often enter the conversation. A wormhole is, in essence, a hypothetical shortcut through space-time, a bridge between places that would otherwise be enormously far apart. The idea has deep roots in the equations of general relativity, though the practical conditions for stable, traversable wormholes appear extremely demanding and probably unrealistic in the actual universe. Still, the idea remains, not as settled fact, but as a mathematical whisper, a suggestion that when space-time is shaped in sufficiently strange ways, the notion of distance itself may become less straightforward than we are used to. Black holes invite such whispers. They invite the mind to consider that geometry might be able to fold in ways too large for intuition. There are charged black holes as well, at least in theory. The Reissner-Nordström solution describes a non-rotating, charged black hole. The Kerr-Newman solution adds both charge and spin. These solutions allow inner horizons and more elaborate structures within the mathematical description. In nature, large electric charge is not expected to remain on a black hole for very long, because surrounding matter would tend to neutralize it. So these kinds of black holes may be less important as common astrophysical objects, and more important as lessons in possibility. They show us how flexible the equations are. They show us that black holes are not just one thing, but a family of consequences. And if all of this begins to feel like a room filling with dim and complicated shapes, then this is a good place to breathe more slowly. Because the universe is under no obligation to become simpler just because we are tired. But we are under no obligation to hold all of it at once. For now, we can let the details drift outward and keep only this much. A black hole is a region where gravity becomes geometry so severe that escape is removed from the future. It may spin, it may drag space-time around with it, it may hint at deeper structures, but at its heart it remains a quiet answer to a quiet question. What happens when space-time bends too far inward? Now let us step backward from the abstract picture and return to something older and warmer. A star. Most black holes begin their lives as stars. Not all, perhaps, but many. And a star is itself a kind of long balance. Gravity pulls inward, heat and pressure from nuclear fusion push outward. For millions or billions of years, the star survives in that balance. It shines because it resists collapse. It glows because gravity has not yet fully had its way. At the center of an ordinary star, hydrogen fuses into helium. In more massive stars, the process goes further. Helium becomes carbon. Carbon leads onward to heavier elements. The star builds layered shells of fusion, like quiet furnaces nested one inside another. Each layer is a temporary answer to gravity, but there comes a time when the answer weakens. For a sufficiently massive star, iron eventually appears in the core, and iron is a turning point. Fusing iron does not release energy the way lighter elements do. It does not support the star's balance. It does not help hold the roof up, so the star, which has spent so long holding itself open against gravity, begins to lose that ability in its deepest center. What follows is collapse. The core falls inward. Electrons are pressed into protons, forming neutrons. Densities raise it to astonishing levels. Neutrinos flood outward. The outer layers crash down, and in many cases rebound in a supernova, throwing the star's upper matter back into space in a bright and terrible bloom. But the black hole is not the explosion. The black hole is what comes after. if the remaining core is heavy enough. This is an important shift in mood. So much of the public imagination connects black holes to violence, to fireworks, to catastrophe. But the black hole itself is not the bright outer burst. It is the inward finality left behind. If the collapsed core is not too massive, it may settle into a neutron star. A neutron star is one of the densest stable objects in the universe, supported not by fusion anymore, but by quantum rules. Neutron degeneracy pressure resists further collapse. The matter there is no longer organized into ordinary atoms. It becomes an ultra-dense state, governed by rules that feel more like a compressed whisper of nuclear matter than anything from daily life. Neutron stars are only a little wider than a city, yet they can contain more mass than our sun. They spin, they pulse, some sweep beams of radiation across space like cosmic lighthouses. Their surfaces are extreme, their gravity enormous, their interiors still not fully understood. And still, even they may not be enough. There is a limit to how much mass a neutron star can support. Beyond that limit, even quantum degeneracy cannot hold the star open. Gravity keeps going. This threshold is linked to what is called the Tolman-Oppenheimer-Volkoff limit. The exact number depends on the uncertain physics of ultra-dense matter, but the lesson is simple enough for tonight. There comes a point where no known pressure can resist further collapse. Beyond that point, the core does not stabilize, it continues inward. And somewhere in that continuation, a horizon forms. This is the birth of a black hole in the most familiar astrophysical sense. Not as a solid remnant, not as a special kind of star, but as a region where the collapse has gone far enough that space-time itself closes the outward path. A star spends its life making light then. In its deepest failure, it may give rise to a place from which light cannot return. There is something profoundly still about that. And because this is a sleep story, because we are not rushing, we can linger near the sadness and beauty of it without sharpening it into drama. A black hole is not merely destruction. It is also transformation. Matter does not simply cease to exist, rather, the familiar ways of describing its future cease to work outside the horizon. The star becomes, in effect, a new geometry. This helps explain why black holes can keep growing. They are not static scars. They are active regions. If a black hole lives near a companion star, it may draw matter away. If gas and dust wander too close, they may spiral in. If two neutron stars merge, and their combined mass passes the necessary threshold, a black hole may form there as well. If two black holes meet, they can merge and become one larger black hole. Growth in the universe is often hidden, gradual, and patient. Black holes are no exception. When matter falls toward a black hole, it does not always plunge straight in. Usually it circles first, forming an accretion disk. The disk is made of gas and plasma orbiting the black hole, losing energy through friction, turbulence, and magnetic interactions. As it spirals inward, it heats up. It can glow intensely in X-rays, ultraviolet light, or other wavelengths. So there is another quiet irony here. The black hole itself is dark, but the process of falling toward it can be dazzling. In some cases, especially around supermassive black holes at the centers of galaxies, the energy released by accreting matter can outshine the entire galaxy around it. Quasars are among the brightest known objects in the observable universe, and at their hearts lie feeding black holes. Again, this is worth holding gently. One of the darkest structures in nature can become surrounded by one of the brightest displays in nature, simply because gravity is so efficient at turning falling matter into heat and radiation before the matter crosses the horizon. And then there are jets around some black holes, especially spinning ones with strong magnetic fields and active disks, narrow beams of particles are launched outward from the polar regions at nearly the speed of light. These jets are not thought to come from inside the black hole itself. Rather, they arise from the violent electromagnetic and rotational processes just outside the horizon. The result can be astonishing: long, narrow streams of energy shooting far beyond their home galaxy, carving through interstellar and intergalactic space. So a black hole may sit in silence at the center, while around it disks glow, jets roar, and whole galaxies feel the consequences. This is one of the reasons black holes matter so much to cosmology and astrophysics. They are not merely endpoints. They are organizers, regulators, engines of structure at scales far larger than themselves. At the center of our own Milky Way lies a supermassive black hole called Sagittarius Astarte. It is not currently as bright or hungry as the black holes in the most active galaxies, but its presence is unmistakable in the motions of stars near the galactic center. The stars wheel around an invisible mass. They move too fast and too tightly for anything else to make sense. This is often how black holes reveal themselves, not by what they shine, but by what others do in their presence. Some black holes are only a few times the mass of the sun, born from individual stars. Some are intermediate in size, perhaps formed through repeated mergers or special conditions in dense star clusters, though this class is still being pieced together. And some galactic centers grow to millions or billions of solar masses. How those giants formed so early in cosmic history remains one of the great open questions. Quasars existed surprisingly early, which means some black holes became enormous very quickly after the Big Bang. Did they start from unusually massive seeds? Did gas collapse directly into them in the early universe? Did mergers build them up faster than expected? The universe has not yet told us the full story. Or perhaps it has, but not in a language we fully understand yet. And this is a good moment to return to quiet. You do not need to hold the taxonomy of black holes in your mind. You do not need to sort the stellar from the supermassive, the spinning from the still, the charged from the likely uncharged. You can let those categories sink away and keep only the broad image. Somewhere in the dark, gravity gathers itself enough to become a sealed future. That image is enough. Now let us move into one of the strangest and most dreamlike parts of the story. Time near a black hole. Time does not behave the way common sense expects. This is not science fiction language. It is one of the direct consequences of general relativity. Clocks deeper in a gravitational field run more slowly, relative to clocks far away. On Earth, this effect is tiny but real. Satellites must account for it. Modern navigation depends on it. Gravity and time have always been entangled. We simply do not notice much in everyday life near a black hole. However, the effect becomes immense. Imagine a spacecraft falling toward the event horizon while you remain far away, watching. As the spacecraft descends, the light it sends back to you becomes stretched to longer wavelengths. This is gravitational redshift. The signals arrive more slowly. The craft appears to move more and more sluggishly as it approaches the horizon. To your eyes, it seems to hover near the edge forever, fading but never finishing the crossing. Yet, the people on board, if there were people on board, would experience something very different. Their own clocks would continue normally. Their own thoughts would continue at ordinary local speed. They would not feel themselves freezing in time. They would simply continue falling. Both stories are valid. This is not a contradiction. It is a revelation. There is no single universal clock shared by all observers in all circumstances. Time is local. It depends on the path through space-time. It depends on gravity It depends on who is describing events and from where. Physicists distinguish here between coordinate time and proper time. Coordinate time is the time assigned from a chosen external frame, perhaps by a distant observer or a mathematical coordinate system. Proper time is the time carried along by the object itself, the time on its own clock. Near a black hole, those two measures cease to match in any simple way. That is one reason black holes feel so close to dreaming. They reveal that what seems frozen from one perspective may be flowing from another. They show that reality can be internally consistent while refusing to offer a single simple narrative. There's a further image that helps. Physicists speak of light cones at every point in space-time. The light cone represents the directions light can travel into the future. In ordinary settings, the future includes options that spread outward in many directions. Near a black hole, the cone tilts inward at the horizon. It tips so far that every future-directed light path lies inward. Inside the horizon, all future paths point deeper toward the center. This means that once you are inside, moving inward is no longer merely a decision. It is what the future is. Just as we do not choose whether tomorrow arrives, an object inside the horizon does not choose whether deeper interior regions arrive in its future. The geometry has taken over. That is such a pure and unsettling thought that it almost becomes soothing. Not because it is nice in the everyday sense, but because it is complete. Inside a black hole, there is no clutter of indecision, no branching of ordinary escape, only one remaining direction written into the structure of time itself. The horizon, then, is not only the boundary of escape, it is the place where the distinction between forward in time and inward in space begins to blur. And still, the horizon is not a physical wall in the usual sense. A large black hole could be crossed without local drama. That remains one of the most elegant tensions in the subject. The boundary is absolute in its consequences and smooth in its local feel. Now we arrive at a question that has haunted theoretical physics for decades. When matter falls into a black hole, what happens to its information? From the outside, a black hole can be described by very few properties: mass, spin, electric charge. This simplicity is captured in the so-called no-hair theorem. All the fine details of what formed the black hole appear to be lost from the outside description. The black hole does not retain visible wrinkles corresponding to the original star's chemistry, shape, or complexity. It settles into an extraordinarily simple state. Two black holes with the same mass. Spin and charge look the same from the outside, even if one formed from a collapsing star and another from a merger. This is remarkable enough on its own. It means black holes are nature's great smoothers. They take complexity in and show simplicity out. But quantum mechanics is uneasy with the idea of true loss. According to the deep logic of quantum theory, information about a physical system should not be fundamentally destroyed. It can be dispersed, scrambled, hidden in correlations, effectively inaccessible for practical purposes. Yes, but not erased from reality altogether, and this creates tension. If a complicated object falls into a black hole, and the black hole seems to remember only mass, spin, and charge, then where did the richer information go? Is it hidden behind the horizon forever? Is it somehow encoded on the horizon? Is it preserved in a way we do not yet know how to read? Or does black hole physics genuinely force a revision in quantum theory? This is the information paradox, and for a long time, it might have remained an abstract clash between principles, except for another profound discovery. Stephen Hawking found that black holes are not perfectly black, because quantum fields fluctuate even in what we call empty space, and because the event horizon changes the structure of those fluctuations. Black holes can emit radiation. This is Hawking radiation over enormous timescales. The black hole can lose mass and slowly evaporate. That single idea changed everything, because now the question sharpened: if a black hole forms from complex matter and later evaporates away into seemingly thermal radiation, what happened to the information about what fell in? If the radiation is entirely featureless, then the information appears to be truly lost. If the information is preserved, then the radiation must contain it in some subtle way, or the horizon must, or the whole framework needs to be rethought, so that the black hole stops being merely a dark object in space, becomes a meeting point between general relativity and quantum mechanics. And the meeting is not peaceful. General relativity says, in effect, that a horizon forms, and what falls inside is hidden from the outside world. Quantum mechanics says, in effect, that the universe should not throw information away. Hawking radiation says that black holes may not last forever. Put the three ideas together and the old harmony breaks. This is why people sometimes say black holes break physics. But that sentence is both true and not true. Black holes do not obviously destroy the laws of nature. Rather, they place our existing laws under strain. They bring deep principles into a region where they no longer fit together comfortably. They show the seams, and perhaps that is more interesting than actual destruction. A cracked map is often more informative than a smooth but false one. Over the decades, many attempts have been made to resolve the information paradox. Some ideas suggest that the Hawking radiation is not perfectly random after all, and that correlations hidden within it gradually carry the information back out. Others suggest that information is stored, in some sense, on the horizon itself, leading to holographic ideas in which the boundary of a region contains the bookkeeping for what lies within. The holographic principle is one of the most beautiful of these suggestions. In very rough language, it proposes that the information content of a volume of space may be described by data living on its boundary, a bit as though the world were deeper than it looks by being somehow flatter than it seems. This idea grew from black hole thermodynamics and later became central in certain areas of string theory and quantum gravity. Black holes, in this view, are not just dark sinks. They are clues to the deep architecture of reality. Then there's the Page curve. Don Page considered how the entropy of Hawking radiation should behave if information is preserved. If the radiation were truly random and informationless, entropy would simply keep rising as evaporation continued. But if information eventually emerges, then the entropy should rise at first and later fall. The curve bends over. The black hole begins, in a sense, to return what was hidden, though in a scrambled and delicate form. This picture does not give us a cozy or simple answer. It does not say black holes politely hand things back in recognizable pieces. But it does suggest that the universe may be more faithful than it first appears. Perhaps the black hole does not erase. Perhaps it delays, mixes, and disguises. That is a much gentler thought, and yet the full resolution remains incomplete. Recent work in quantum gravity, entanglement, and holography has made the Page curve story more convincing, but the subject is still active, still debated, still full of subtle assumptions. Entanglement itself may be part of the answer. Quantum systems can be linked in ways that do not resemble ordinary classical connection. Some researchers have even speculated that space-time geometry and entanglement are deeply related, that connections in space may emerge from connections in information. There is a famous shorthand for one such idea, that wormholes and entangled systems may be two descriptions of something connected at a deeper level. Whether or not those exact proposals endure, the spirit of the work is clear. Black holes are forcing physics toward a more intimate relation between geometry and information. And if that sounds abstract, it is, but it is also strangely lovely. It suggests that what we call space may not be the deepest layer of reality. It suggests that the universe might be woven not only from locations, but from relationships. Then come even more speculative ideas. Could singularities be avoided in a final theory of quantum gravity? Quite possibly. Many physicists expect that the infinities of classical relativity are signs of breakdown, not ultimate truth. In some models, collapse might end in a bounce. In others, space-time may become discrete at tiny scales, preventing infinite curvature. In still others, the interior of a black hole may be replaced by a more subtle quantum state with no classical singularity at all. String theory, loop quantum gravity, causal structures, emergent space-time proposals, all of these are attempts to go beyond the smooth but incomplete language of general relativity. None has yet delivered a fully settled final answer accepted by everyone, but each is an effort to listen to what black holes are trying to tell us. And perhaps that is the most restful way to think about theoretical physics, not as a war for conclusions, but as a listening practice. The equations speak. The universe responds. Observations trim the possibilities. Theories stretch and break and are mended, and in the middle of it all, black holes remain patient, saying very little directly, yet forcing us to ask better questions. There are even more dramatic proposals at the edge of the conversation. Some have imagined that the event horizon might not be smooth after all, but replaced by a firewall. A zone of violent quantum energy that would destroy anything trying to pass through. This idea arose from attempts to preserve certain principles simultaneously, but it remains controversial. Many physicists regard it as a sign that some assumption in the argument needs revision, rather than a literal feature of nature. Others have considered white holes, hypothetical time-reversed cousins of black holes that cannot be entered from outside, but from which matter and light can emerge. White holes are mathematically permitted in some contexts, but none has been convincingly observed. They remain, for now, part of the universe's unused grammar. Still others continue to wonder whether wormholes might exist in some limited or non-traversable sense, or whether the inside of a black hole could connect to new regions in ways we do not yet understand. These ideas drift at the boundary between rigorous theory and imaginative extension. It is good to keep them in that boundary. We do not need to believe every mathematical possibility, but we also do not need to deny the wonder of what the equations allow us to imagine. And now, after all this, we can come back to the question we began with. Do black holes break physics? The gentlest honest answer is this. They do not seem to break nature. They seem to break our neat separation of theories. General relativity works astonishingly well for large-scale gravity. Quantum mechanics works astonishingly well for the microscopic world. But inside and around black holes, especially near singularities and horizons, the two are forced into intimate contact, and there, our present understanding becomes strained. So black holes are less like vandals smashing the laws of nature, and more like mirrors showing us where our current laws are incomplete. They reveal the unfinished edges of our map. They are darkness used as a diagnostic. They are silence turning out to be information. They are the places where the universe becomes too deep for our easiest sentences. And because this is a story for sleep, we do not need to sharpen that into a climax. We can let it remain soft. We can let the answer stay open. Perhaps black holes are not the end of physics. Perhaps they are the beginning of the next layer. And perhaps that next layer will not arrive as one grand final revelation, but as many patient small clarities. Better observations, better mathematics, better ways of asking what space is, what time is, what information is, and what it means for something to be hidden. There is something tender in that possibility. The universe has not denied us understanding. It has only asked us to grow quieter and more careful before it gives the next part. So let us gather the whole journey one last time, slowly enough that it can dissolve as we say it. Gravity is not only a pull, it is a shape. A black hole is not only darkness, it is a region where that shape bends too far inward. The horizon is not a wall. It is a boundary in what futures are possible. The singularity is not simply a thing. It is where our present theory begins to fail. Stars can live for ages by balancing gravity with fusion, and black holes can be born when that balance is lost beyond recovery. Black holes can grow by feeding, merge with one another, launch jets, guide galaxies, and reveal themselves through the motion of nearby stars. Near them, time slows differently for different observers. Light is stretched, futures tilt, and deep inside the whole subject waits a question about memory, about information, about whether the universe ever truly forgets. That question remains unanswered in full. But unanswered does not mean empty. Unanswered can be fertile. Unanswered can be beautiful. Unanswered can be exactly the right companion for a night like this. Because sleep, in its own way, is also a crossing into a region where not every thought returns clearly, where the bright outer surface of things softens, and where it is all right not to solve what remains. You do not need to go beyond the horizon of this story. You do not need to follow the equations where they fail. You do not need to decide between relativity and quantum theory before morning. The universe can keep those problems for a few more hours. The stars can continue their quiet turning without you. The black holes can go on, bending time in the dark. The galaxies can keep circling their hidden centers. And you can rest. If some part of your mind still holds the opening question, then perhaps let it settle into this gentler form. When black holes seem to hide everything, maybe what they are really hiding is not only matter or light, but the doorway to a deeper understanding of reality. And if that deeper understanding has not arrived yet, that is all right. The dark has always been part of learning. Seeds grow there. Stars are born from cold, hidden clouds. And maybe physics, too, sometimes has to pass through darkness before it finds a clearer dawn. So let the details dim. Let Karl Schwarzschild go. Let care go. Let horizons and singularities and page curves and entanglement loosen their grip. You do not need their names anymore. Keep only the softness of the images, a star holding itself open for a long time, a final inward fold, a dark center around which other things move, light growing tired as it climbs away, time becoming deep and strange, a universe patient enough to keep its secrets for billions of years, and your own small room, safe and ordinary, held quietly beneath it all. That contrast is part of the piece. Far out there, black holes curve the structure of reality. Here, close by, a blanket rests over a shoulder. A wall waits in shadow. Air moves in and out. The night asks nothing difficult of you. You are allowed to stop thinking now. You are allowed to leave the unfinished parts unfinished. You are allowed to trust that the universe is still there, even when you are no longer paying attention to it. In that sense, perhaps sleep is our gentlest practice for cosmic humility. We close our eyes, and the world does not vanish. We let go, and reality continues. We step back from the need to watch everything, explain everything, solve everything. And the universe, vast and curved, and mostly dark, goes on by itself, somewhere above, beyond weather and cities, and the pale scatter of local starlight. There are places where ancient matter collapsed into blackness, and the future narrowed to a single inward path. There are disks of hot gas circling invisible centers. There are quiet giant masses in galactic hearts. There are waves from old mergers still traveling through space. There are equations not yet finished, questions not yet answered, horizons not yet crossed by understanding. And none of that needs anything from you tonight. Let it all remain out there. Let the cosmos keep its patient work. Let the laws of nature continue their long conversation in the dark. You can drift now. You can fall through the softer horizon of sleep, where not every signal needs to come back, where thought becomes dimmer and kinder, where the mind no longer tries to hold the whole sky at once. If black holes are the places where light cannot return, then sleep is the place where effort does not need to return. Only rest, only quiet, only the slow closing of the day around you. The universe will still be here in the morning, with all its curved mysteries intact. Black holes will still wait in silence. Physics will still have its unfinished edges, and somewhere, perhaps, the next answer will already be forming in the dark. For now, though, you do not need the next answer. For now, the feeling is enough. A deep, patient universe. A safe, dim room. A mind no longer required to keep watch. Good night. Sleep softly beneath the quiet weight of the stars.